This podcast is supported by Siemens, your partner for industrial-grade AI.
Hello, everybody, and welcome to a new episode of our AI in Industry podcast. In this episode, Peter talks to Philip Wouters from TangentWorks about instant machine learning and time series. Peter, the stage is yours. Enjoy listening.
Hello there. I'm sitting here with Philip Wouters. That's, I believe, the right pronunciation, Philip, right?
That's right.
From TangentWorks. So let's start with you tell our listeners who you are, Philip.
Yes, hello everyone. My name is Philip. I work at TangentWorks. Our company is in the predictive analytics space. My role there is as customer success manager and value engineer. So we provide predictive analytics in the form of forecasting and anomaly detection capabilities through our product called TIM, the Tangent Information Modeler.
TIM. What does TIM stand for, you just said? Maybe one step slower.
Yeah, so the Tangent Information Modeler, it's a forecasting or a time series modeling solution that allows you to do the two difficult parts in time series, which are feature engineering and model building. It does that for you fully automatically. And we've wrapped that then into a useful platform that can be easily used. So that's what we bring. And that's also what we bring together with Siemens, which is the reason why we are here.
Right. So fully automatic is what you said. Is that the USP? Or, how would you say? How do you sell your product, so to say? Is that what makes your product, your solution, different from other solutions?
Yes, definitely, because time series in itself inherently is a very, very complex task. I'm sure that the listeners that have dabbled in time series will certainly agree. So to do all of that work manually and finding those features that actually have predictive value, that's really the most complex part. And we noticed that which has also been said in this event here, if you want to really bring value with AI, you need to be able to scale. And scale comes from automation, in our opinion. So that's indeed the USP that we bring.
I've just been looking over an interested potential customer's shoulder as you were kind of demoing your solution, I believe. I did recognize I've been involved in looking into time series myself a couple of years ago. Tell us a little bit on the background. So I would recognize time series out of, whatever industrial, or you can tell us what your typical market or application is. And so how does a potential user work then with your tool, with your service?
Well, the potential users, they're very broad. So we have users in all kinds of sectors. We originally came from the energy sector because there's a lot of time series there. But then we noticed that time series is really everywhere. And big focus right now is in IoT. And that's also why we partnered together with Siemens, because there's a very big opportunity in IoT there. And it goes all the way to finance, to sales forecasting, and those types of use cases that we cover. Now, a typical user of our solution, they have also a very flexible way of using TIM. Either you use it through a platform that we've developed ourselves so that you can interact with the solution, or you have a completely automated way of using TIM where we have pre-made packages where you can simply let data flow through and generate results for you. So yeah, we try to remain as flexible to the differences that exist in time series to accommodate for all of them.
So let's look at an example maybe in industrial environment. So who is the typical user? I think your approach, we'll come to that later on, is to empower the domain experts. So is that, you say energy, let's maybe stick with energy. Is it then about, the windmills producing data, and who is then the person sitting maybe in the control room and they get data, and what do? You like predictive, or do you look backwards? Why did a mill break down? Or
yeah, those are both good examples. Indeed, we have examples of wind turbines being analyzed by TIM. So indeed, what you could do is forecast the power output of a windmill so that you can use that to balance the grid, for example, that information. And then the user there which are often data science teams that just package all of the data across all of their wind farms and then let data flow through their models, which then TIM would provide. So that's often the data science teams that are working with our solution in that particular example.
Is it always the data scientist, so to say, or do I understand your solution also to be made available for people who maybe get a day's training, but they haven't had like a typical data science. We haven't had so many data science courses, so to say. So is it for the data scientist only with all the base knowledge, or do you say you offer your solution at a, let's say, higher level as well?
Yeah, so definitely the higher level also exists, although the demand comes mostly from those other teams. However, an example of people that are using it which don't have a data science background are often in finance. So for trading purposes, for example, that's where we see business users really generating the predictions using TIM either manually or automatically, and then adapting it to whatever needs they have.
Just before we started, we mentioned AutoML, and you suggested it's not AutoML, but there is some kind of low-code, no-code direction towards this, what I call the domain expert? Or?
Yeah, indeed. So with this, our technology, we call it instant machine learning, instant ML, which we see it really as a next step in the process of automation. So it all started with, of course, handcrafted models. Originally, data science will really dig deep into the data sets, try out different modeling techniques on their own, and trying to find out whatever predictive value they have.
They were like alchemists, right? Is what I
something like that, indeed.
Putting all these parameters, and only they would know what parameter to put.
Exactly, and that works fine, and it's definitely a good way to learn about your data. However, if you want to then scale, that becomes very difficult because you need intelligent labor and you need to create a lot of models. And one way that people try to solve that is with automation through AutoML. However, there is a big drawback there, since they apply brute computing force to just run your data through a couple of hundred modeling techniques, which then generate a couple of hundred models, from which you will actually only use one, which will be the best one according to them. And that also works, but it's very resource intensive. And we solve that by creating our very own modeling technique, which is specifically designed for time series. So you can still use AutoML for other cases, but if you really want to tackle time series correctly, we say that instant machine learning using our TIM is the right way forward. You actually only create the one model, which is specifically designed for the case, with very limited computing resources.
Wow. You would say that it's more like a push of a button by a person who knows how to handle your software, your application, and it will go through automatically, which is the base idea. But you don't like, or you have an improvement on one specific section, which in these times of climate control and the need to reduce energy, can you put a number to that? Yes, I understand. So it could be that AutoML uses, maybe there's still a parameter if it's running 50 or 100 models, but can you give a number to that? Is it, instead of, I don't know, using 1,000 watts, you're using 10 watts? Or, is that...
Well, we actually have a very concrete number that we can share. I don't know it by heart. We did that analysis a couple of months ago, comparing ourselves to the resources required with AutoML. That's all on our website and in our content that we share at with Tangent.works. So you can check out the real numbers there, but the speed of execution is dramatically better. So where a model is being built in a matter of seconds, it could take hours and hours with AutoML, and then associated the computing time with that, you can calculate the numbers from there.
I don't want to put a number in your mouth, but it sounds like a factor 100 or something, or could be higher. I don't know. If you go from seconds to minutes or hours.
It's very use case specific, of course, but we see a lot of use cases where it's indeed 200 folds in those parameters.
That is very interesting. Yeah, in the area I've been working in myself, not as the person to be the data scientist, which I'm not, but it was like running on like a notebook. Then you can say, well, does it really matter if it's seconds or if it's minutes? Sure. And if it's the difference of, is it then hours, which my colleagues, data scientists, were running, if you can bring it down from hours to seconds, as you say, then it, of course, does help a lot. So let's look a little bit under the hood then. Not too far, but because, most of our listeners are not math specialists or even data scientists. I'm sure we have those as well, but not all of them. So how does this then work until the level that many of us can understand it? Most of us understand the AutoML way. I have all these different mathematical, typical machine learning and or other models. I run all of them. There are certain ways of checking how good they are, and in the end comes the best. I think most of us understand that. What is the I think you used the word secret sauce. Is that correct? What is your secret sauce behind doing this?
Yeah, so the secret sauce is called information geometry. It was a topic that was the subject of I believe, the doctorate of our CTO. So he studied that while he was doing his doctorate, and he noticed that this can be applied to machine learning and to time series specifically. So that's where the mathematics comes from, and we're actually unique in using that. And what that allows you to do is that speed of execution and that automation. So we then use information geometry to do the feature engineering again, which is, as I mentioned, the most complex part. So really finding within the data what are the actual patterns, and from there you can use any modeling technique to put those together into a model. And what we use are GAM models, generalized additive models.
So you stick to that model, which in, as a general AutoML, that could be one potential model of the many different approaches that you have. But you typically say when there's time series, that is the one that you prefer, or that's where you believe that brings the best.
Yeah, exactly.
If you know which the features are that you need to put into, that you need to look for.
Yeah, and for that search, we use our modeling technique.
Right.
So that's the key in time series is definitely feature engineering. Once you get that right, there's many other approaches that you can take. We've chosen our approach after the feature engineering, but their big innovation comes from there.
Okay, I must say it's new to me, but I'm not at that level, that detailed, but it's very interesting to hear, I must certainly say. Because, you know, Robert and I, we have been talking about AutoML many times, and then there's friends from us, including people teaching students, like a professor, for example, who are not always believing in the approach of an AutoML, and you go one step further. You already have a solution that you're selling. We talked a little bit about that. So how would I use it? Does it run in the cloud somewhere based with a certain partner? If I don't like that for whatever reason, we started 3 years ago, and before that time, 9 out of 10 industrial companies, but maybe it's the same in medical, even stronger. They would say, my data does not get to the cloud, and then we have solutions like federated learning. So there's a lot of things happening there. But where does your solution run?
No, that's a very good question. We acknowledge that as well, that there's so many different options and so many different companies that really are in demand for those different options. So our solution was there just to remain flexible. Our solution is containerized, so we can actually deploy it in different environments. Our standard way of using it is through the SaaS, as a SaaS offering really. So we use our cloud environment to offer access to our solution. And from there, we can also deploy on other people's clouds. So if you want to have it within your own cloud, that's possible.
Oh, so you have an own or another one?
Yeah.
They already have a certain agreement with one of the big ones or a smaller one. I mean, as long as it's containerized and you can put it in there as well.
And then one level beyond that is also if you want to have it on premise, that's the same process really. There's even an application on edge devices. So if you want to bring the model really to the machines, that's also possible. And it's simply because of our technology is so lean on computing power, you can put it on the machine.
That's both for training as well as for inference. I mean, inference is always...
So mainly inference, of course, because that's where the demand is also. But it's also possible for model building, yeah.
I must say, and again, I was not the one, but I've learned from my team doing it. And we always would. And the other discussion was always about, and we've had like 10 years of big data. We still have big data, but the other discussion is the small data. And we've been dealing with that topic for a long, long time. As already at that time, 5 years ago, we would take, let's say, terabytes of data. And just as an example, and maybe we would have 100, 200 values, and we would, through statistical approaches, in my understanding, bring them down to, and maybe that's the feature engineering, to the 10 that the statistical environment, maybe similar approaches at what you have, I don't know. And there was those were the 10, and we didn't need the other 140. So we'll bring them down to a couple of megabytes, a couple of 100 megabytes. And my colleagues would therefore run on notebooks. So we're looking here at and maybe that's the question then. So time series, again, terabytes, zettabytes, is that a similar thing where relatively early in the process you find out which are, your features or your relevant features, and for that reason you only need maybe 1% of the data that's relevant, or?
Yeah, so the big data question is one that we get a lot. And it's something that we're actually not that worried about at all, because in fact, in time series, the big data doesn't really happen. At least for unique time series, you only see datasets which maybe have a couple tens of columns and then a couple of 100,000 records. That's the sizes that we typically see, which don't add up to that many megabytes. So our solution covers that quite easily. Of course, we do have scaling capabilities to tackle very large scale use cases, which then have maybe a couple of 10,000 of those size datasets that you want to analyze, maybe in parallel, maybe in other optimized way. But time series inherently doesn't require these big datasets. If you, for example, do image recognition and apply AI to that, you get better with more data. With time series, you actually don't get better with more data because old data could be irrelevant and new patterns might be better for performance. So you want to focus on the latest information, which is often more valuable.
Right. So after you found out which your relevant features, that's a double up or not. I mean, features are always relevant, I guess, but maybe you have more relevant ones than the other ones. I don't know. Yeah. But as soon as you know them, if you have then your solution running in the production environment, then it's actually only those that you need the values of, right? Is that right? I mean, if you sit down the feature extraction and say those are the 10, but you're getting, same thing, 200 values out of your production line, you do not necessarily need to feed those 190 into your solution, or?
Well, I would actually say no, because of structural changes and model drift. So what we often see in time series is that the data itself changes over time. A big example of that is, of course, the COVID pandemic. There, a lot of time series data sets changed dramatically. So what you want to do is remain adaptable to those changes, and maybe a factor which was not relevant before might now have a lot of predictive value. So what you need is something that remains adaptable to the changing situation. And the way that we solve that is through continuous retraining. Because of our modeling technique, a model is built in a matter of seconds. So the model actually becomes a byproduct and you focus on the results really. Now that translates itself into every time you need a prediction, you just build a new model with whatever latest information gets added to your dataset. So if there is a new pattern in the data, you pick it up immediately. And we have actually a very clear example of that on our YouTube page, which you can check out. And there you see the difference between a one-off model built with then inferences based on that model created by Tim, compared to continuous retraining created by Tim. And there you see that the results dramatically diverge over time, which is just model drift visualized. Exactly.
Tell us a little bit about the model drift as an example, how that's happening. I mean, I can share one example myself. We were looking at 1.5 years of data of a very specific machine. And then, in the meantime, as we were working with them, they had changed a very structural part out of this very complex machine. And then they expected us to just continue. And we said, oh, that's really tough because now we cannot use the data of the 1.5 years. So that's one example that I understand. Sorry. Give us another example of what you call model drift, how that comes in. Maybe you stick to the corona or something else in the industrial space.
Yeah, so the example that I just mentioned on our YouTube page is again in the energy space, because we have access to data from there. And there we forecast the consumption on the Belgian energy grid, so total consumption within Belgium, which we then work with weather data and public holiday information, which are always useful predictors to create an accurate model. And that just gets continuously updated over time. And then we build a one-off model at a certain date, use that for the rest of the predictions, or we continuously retrain with new information coming in. And there you see exactly that model drift. So the energy sector is a big example. On machinery, we've had that question also from one of our customers. So that's what we're working on as well. And in the finance industry, that's also very relevant because, for example, Fed hikes, which is now very actual, when the Federal Reserve or the European Central Bank changes their interest rates, that's a big structural change.
Oh, okay. So then your model is going to change structurally different. So then somebody needs to push a button to have it rerun, or
no, fully automatically.
Okay, so you're reading in your values, and if the values have a structural change, that's a trigger to have the complete model retrained.
It's not really a trigger. It just happens every prediction you build. So you actually have a clear visual that we built, where you just see the current model. And if there a structural change happens, it's already been taken into account.
You have a continuous model like
Model
seconds or milliseconds, or I don't know how you put it.
Depends on the use case.
All right. Oh, that's amazing. That's really amazing. Yeah. It's obvious that I didn't understand that just until a second ago. Great. Wonderful technology. Tell us a little bit about your company. So you said you're based in Belgium, right? Where are you based?
Right. So we have two co-founders. One is Belgian, one is Slovak. So the Slovak has invented the technology rather. So his team is in Slovakia there. And then the commercial side is more in Belgium, but we're also spread around the world. We're trying to explore the US market now and are also available in the UK and across Europe, of course. And yeah, that's the commercial side of things for TangentWorks. And we mainly go to market through partners. So we're really looking for companies that want to tackle time series and embed our solution within their solution, which one of the big example is Siemens, of course, through then MindSphere, because Tim is now actually under the hood working within MindSphere as the AI for everyone. That's what it's called. So you have Tim available there.
Okay, so those listeners that have already Siemens working, they already have access to you, basically.
Yes, if you can access MindSphere, you can access Tim, I assume.
Right. Other ones that are interested, they will find their way through to your website, TangentWorks. And also you say interested potential partners. I'm sure they can find their way to you through the website, right?
Yes, I'm sure. I'm not sure if my contact information will be shared through the podcast, but we're happy to connect. If you're really all about time series or working with time series, then we're definitely happy to discuss.
Sounds great. Thanks a lot for your time and good luck with your solution. Sounds very interesting.
Yes, thank you.